Good morning, everyone. So I'm going to talk, as Kel said, about something that has to do with my European Research Council Consolidated Grant. Still 2 years to go. And it's a new kind of, let's say, if we want to put it in a nutshell, it's a new theory about autonomous, interactive, real-time systems. So let's see a bit the thing. So let's make a fast forward to 2030. So we assume that we're going to have all these cyber-physical, because the pointer doesn't work very well, cyber-physical, mission-critical, interactive systems, okay? So then think about swarm robotics, self-driving cars. Okay, we read about them, but we don't see them. Smart Internet of Things, all these kind of nice things. This is going to create a network of intelligent systems. So we're going to have intelligent systems with capabilities of processing, learning, sensing, and communicating, okay? And they're going to be networked. What they're going to need? They're going to need reliable, real-time communication capabilities. They will have to interact in an automatic way, ideally, and they will have as well to arrive to consensus, to do some actuation, to do some decision-making on a timely manner, okay? And if there's a decision-making, if this comes from, let's say, an AI algorithm, we also want to have some explainability and trustworthiness. So this is going to be the new, let's say, ecosystem that we're going to, okay? So think about this. This is Arc de Triomphe in Paris. So think about, or if the pointer works, think about having all these cars converging, and you have them as autonomous self-driving cars. There's no driver, and you hope that they could do that. Okay, let's put radar, LiDAR, have cameras, all the signals, and they'll have to exchange information. Now, if you want to arrive to timely consensus, if you want to do this collective maneuver at the same time, sending all the information that you have to the others, like broadcasting all the information, receiving all the information, trying to do some processing, even if you have very nice processing capabilities, you won't arrive at the order of milliseconds, for example, at some kind of decision-making or collective behavior, okay? And we have to see where is the problem. Probably you can do it, let's say, for 1, 2, 3, 5 cars, okay? People will say, okay, we have 5G, we can do ultra-low latency and reliability and so on. Yes, for few cars, but is it scalable, okay? That's the big question. So in the future, while systems will have to cater for systems, for applications and services that they will want to acquire, process, and transport massive amounts of data. Think about the industry 4.0, all this automation that we have. And this is going to come from a bunch of, a huge number of IoT connections, okay? You're going to have constraints, energy, we're coming back to that. So as Matthias said, let's try to save some energy. Here, I'll tell you, let's try to save sending useless information. This is my talk, basically. And we're coming to the same kind of, let's say, paradigm that we want to say. You have also to save on network resources, computational resources, all that stuff. It has to be scalable, okay? And then you're going to have to deal with data that come from different modalities. You have multimodal data, you have high-dimensional data, and also that they are geographically distributed. And if you want to do some decision-making, you have to fetch them, basically. Okay? Just put some numbers here. A car, for example, that collects information about the street to detect pedestrians and so on, we are on the order of, here it says like few terabytes, basically, per day. So now the big question, and this is what I'm going to propose, is like, do we know how to do that in an efficient manner? The second thing, do we have the right theory first, and then the algorithms to make it work? Okay? So make a step back and go back to the sources, and then say what we have done so far. And basically, the digital revolution in every device that we have, and communication, compression, computer, so on, the theory behind comes from this guy, Claude Shannon, basically, who back then, in 48, if I recall well, says that, okay, the problem has three, basically, components. It's a problem of reliable transfer of information. We have a source. we have a transmitter, we have a channel, we make a statistical representation, and then we reconstruct the source as exactly as possible at the destination. Now, of course, the messages we're sending have some meaning and have some effect on the destination, what we call semantic or effectiveness. And he did a very nice master stroke, basically, taking deliberately semantics out of the picture, because it's a very difficult problem to tackle, and this is what we're trying to tackle today. So he focused only on the noise, basically, and the equivocation, and he said the problem is basically how to reliably transmit information. There's another thing as well, the number 3, that sometimes we'll forget, is that the encoder and the decoder are centrally designed. So we have decided about the protocol. We have the same kind of alphabet. Messages come from the same alphabet. Now, if you put agents, if you put different cars, different systems that come even with different versions of software, and you want to put them together to talk, there's no central design. They have first to find out how they can communicate as well, okay? This is a big assumption that sometimes we forget. Now, from this theory, and it was successful because this is basically what we have today, the mobile phones and so on. We bring it into practice to the 2G, 3G, 4G, and so on. But my claim here is that the way we design the systems in practice is what I would call a maximalistic approach. So normally we want high rate, we want less delay, and so on. Let's try to boost basically everything. Let's try to inflate the requirements. Some people are having this anecdote that say, okay, every new generation you just multiply by 10, 100, and so on, and just you have a new generation in your key performance indicators. What we're doing is we over-provision to make it work, okay? So basically, we're gonna put more resources than probably we need to make it that. And the claim here is that this is not sustainable, it doesn't scale, okay? Now, back then, there was an introduction as well to Shannon's work from his boss, basically, Weaver, in 49, the introduction of the seminal paper of Shannon. We said, okay, ideally, the problem of communication have 2 other levels. The level of semantic, how precisely, basically, the symbols convey a certain meaning, and the effectiveness one, some people call it the pragmatic level, how effectively, basically, the behavior of the receiver change, okay? Now, that was fine, and many people tried to build what we call semantic information theory and tackle these problems. The thing is that we never had any theory that has an operational meaning, give us some practical systems, and it's a very hard problem. For example, you have to deal with meaning, you have to talk about logical probabilities, truth functions, and the theories, beautiful as they are, they have a lot of inconsistencies. So let's schematize a bit with some abstraction. So Shannon's model, basically, the basic thing is that traffic is exogenous. Somebody's giving it traffic. So basically, communication engineer, people that are on communication on the physical layer say, okay, I don't care what they transfer. Somebody's giving it traffic. For me, it's a random sequence, a sequence of random bits, basically, okay? And people are reasoning in terms of pipes. I have a pipe where there's a flow of information, and I want to make the pipe fatter and fatter. Basically, I don't care what they transfer, basically, okay? And then the metrics that I have, throughput, delay, some quality of service, and so on. And normally, I want to do some non-causal signal reconstruction, and in general, I reconstruct the whole information flow, and then I let the application layer decide if it's what they want. So basically, I receive information, that's okay. I receive a bunch of megabytes, but finally, this is the piece of information that I need to keep going. What we propose with this goal-oriented semantic communication, it's a unification. We start already from the data generation. That the pointer, I think, doesn't work very well. Okay, so we start already from where traffic is generated. So we select the traffic, or let's say it differently. We have a goal. Where we communicate. Communication is to do certain thing, a certain task, a certain goal, if you want it, for a higher thing. So knowing that, I'm going to go and select or generate at will the traffic that I will need, the messages or the packets that will serve this goal as effectively as possible, okay? So I will start already from the data traffic generation, because I see a certain process, okay? I see a certain source that has some kind of evolution, okay? So I know that certain things are more important than the others, and this is what I'm gonna transfer. So, and this is a joint, I mean, we can show theoretically this is a joint optimization, joint design problem. It's not separable. It's not like take your best data acquisition and processing algorithm, okay, you put it, then put your best communication algorithms, transmission schemes, and then you put the reconstruction, you put all together, it will work. It doesn't work like that. It has to do it in a joint way, okay? And the key for that is to take into account what we call the semantics of information, basically the significance or the usefulness of the data with respect to the goal of the data exchange, okay? And this is key if you want to do some kind of real-time reconstruction and some even fast reconstruction for cases that we don't even care about having the entire information flow. You have a car, for example, you have a self-driving car. You want to brake. You don't want a lot of information, you want a command, but you want it on the right time, on the right window, otherwise it's useless. Are we able to do that? That's the thing. So, now the first point is to define what is the semantics of information. And this has been a lot of debate, let's say, because semantics is a term in linguistics that has its own term, its own definition, and people are used to that. It has to do with meaning. Now, in my case, I'm also Greek, so it comes from the ancient Greek, which is important, significant, okay? And for us, semantic here is not meaning, it's the importance of information and the significance of information, okay? Now, the big problem is how we define it. We came out with some kind of, three kind of granularities in different resolution. The first thing is you have to go at the source of the information, okay? This is the nuclear part. I would call it macroscopic, inspired by physics, let's say. So certain outcomes, certain events have more importance than others, okay? In the same, in the information theory, it has to do with how, with the surprise sometimes, we'll say, okay, how improbable is an event. If it's a low probability, then we get more information. Now, you get the simple example. You have, somebody tells you it's gonna have a snow on the Sahara Desert. Low probability, a lot of information we gain. But you won't do something. Probably you wanna text it to your friends, but that's it. Now, somebody tells you it's gonna be a heavy storm at your house right now. It could destroy everything. Same low probability, let's say, but what you're gonna do is gonna just leave and go and protect your house. So two, let's say, events that they have the same content of information with a traditional way have different importance for us and will affect the system differently, okay? We need to be able to capture that. Now, this then, you're gonna put it on a link level and a network level, and then it's gonna have to go into the information attributes, and I'm gonna define some of them. We're gonna have to find the quantitative metrics of information, entropy, as usual, and the qualitative, depending on the context, the application, and so on. And there's a third one, which is a bit more futuristic, which I will talk with the last slide, and it's a glimpse also to physicists as well. Now, how to quantify the importance of an event? There are many ways. One of the things is that we try to incorporate this disparity between outcomes of the same probability, and one way to do it is basically to put some weight or some utility function or some generalized function into the entropic metrics. Entropy is still there, so that's one approach to do it, and then you can go into the classical way of basically have a source which has the content, the traditional entropy that we have, but also have an entropic metric that measures the importance of the information, and you can solve your problems. This is still a classical way of going, but we're still not there because normally entropy measures the average uncertainty, but sometimes we care about the exact, basically, outcome that we're gonna have. There's a lot of connections with other theories, so I'll close the parenthesis here. That's one promising direction, but still we're lacking formal metrics that will allow us to quantify the same way entropy quantify the content of information. to quantify the importance of information. We're getting there. Now, we can take a more, let's say, engineering approach, inspired by something which is called age of information. So we can say, okay, we have certain information attributes. We have attributes that they are inherent into the, the source. These are, for example, freshness. How fresh is the information? And it's a very simple definition of how fresh is. When it was generated, okay, it's the difference between when you receive it and when it was generated. Some people reasoning in terms of delay, okay? But this is not everything. Suppose that you have a very fast connection and a very slow one. Most people say, okay, I care about the fast. But then if you want to make a decision making, and in the fast connection, you transport data that came from yesterday. But in the slow connection, even if it arrives supposedly later, you transport data that are just 1 second before sample. Which one you will choose? The one of the slow connection, not the fast one. Because what you care is to have fresh data, a fresh representation, and an updated representation of what, let's say, one net sees, so that I can take a decision making. Okay? You have precision, accuracy, but then you have contextual attributes. You can have fresh information that for some application, a certain amount of freshness is fine, but for some application, you are very picky, you only have to have it in a certain window. And this depends on the context of use. Okay? And this comes as well that for some people say, okay, but where's the meaning here, where's semantic, and so on. We use this what Wittgenstein say. Basically, the meaning is context, is in the use of information. Even when we talk, to understand each other, we have to put it on the context. So even the meaning has this context. And the context is another problem that we have, how to formally define and have tools about the content. You also see you have some kind of information value duality. So you can have attributes that they are contextual and innate as well. And on the top of that, you have some perceptual quality, okay? How you perceive as a user with respect to your requirements, to your application requirements, to your goal, how you perceive basically the representation of the information. So a very simple thing to do is the semantic information is basically a composite function when you have, let's say, a vector of the different attributes connected together, and then you can also have a context-dependent cost-aware function. We can go as general as possible. Just to give you a simple example. Suppose that I care about two metrics. The first one is accuracy, the distortion. So this one, xt minus xt hat squared. I also care about the information freshness or age of information, as I said. So when I receive a packet minus when it was generated, not when it was sent, when the information was generated. Okay, I'll just take a multiplicative factor, and then I have the contextual function, which is a timeless, which is as long as I receive it within that, I guess, yeah, okay, it works. Within that kind of time window, my utility is constant, and then it's exponentially decreasing. Okay, that's some function. And then you can recover all the metrics that we have, age of information, nonlinear age of information, value of information, people in control use a lot of value of information, quality of information, and so on. Okay? So we took that, and what we did is we take a system, a multi-user one. We have a phenomenon here. We have a physical phenomenon. We have sensors observing that, multiple sensors, and they have to send it to different monitors, which will have heterogeneous goals, different goals. And then we say, okay, the importance has to do is a function of the probability of occurrence. I can define that the most probable events what I care, or the less probable events what I care, for example, for the sensor. So if, for example, my system works in the normal mode, I don't care much. But if not, then I have to keep going. I will skip that because in the interest of time, I think I'm going a bit slow. What I want to show you here is that, for example, you have 100 realization. If you play your tricks about caring about what is important information, how you achieve your goal in a better way, then you can, depending on your traffic, you can send just 10 or 20 out of them. So you can save a lot of things. Yeah. Now, 5 minutes. So I have to bring something else as well here, is that if it's goal-oriented, if the goal is given by the observer or the end user, this is basically the king now, or the queen. So suppose that I have Alice, who collects the data and wants to send information to Bob, okay? Bob has a goal, okay? So Bob will query information when he wants. It's not like Alice sees the source and says, okay, I have something important to say, but Bob, who is the decision maker, says, I don't care now to have this information. I want it later. Or I want it when I have a decision. I have a doctor that, says, I don't care. Every 1 hour, I'm going to take the measurements of my patient. But now Alice sees also the process. See, the patient has some abnormal thing. So he has to send feedback. And Alice doesn't know, has an estimation of the goal, has a belief about the goal, and he could learn the goal of Bob. And Bob has an estimation of the data because he doesn't see the source exactly. He sees what Alice is sending, actually, okay? It's partially observable, the system. Okay, so basically here, what we need to do, we need to do some kind of Bayesian aspect of the thing. I'm going a bit fast here, forget the equation. And then we can define basically based on the belief that I have between the goals, the data, and so on. We have Bayesian agents that basically we're going to redefine mutual information entropy and have some interesting properties that information theory doesn't have. For example, I have no data processing inequality, which means data could add information because more data does not improve the information in the classical way. I can also that processing helps and so on. Okay, we did that with a simpler example of this. We're still building that. And basically we taking into account the query and the pull base because what is changed from the traditional way of pushing information is not like information generated and pushing it on the other way. Is that is the end user, is the observer when he's going to pull information. It's a pull-based model where only when I ask information for me counts. The rest that you send me probably not. But this is also a bit of myopic approach because also might ignore what happens in the real field. And there is this kind of game to play here, okay? Since I have very few time, I'll skip that and I go to something of the bigger problem, okay? So I started by saying that this is a communication theory, but it turns out that the communication problem per se is getting less and less relevant. It has big interplays with learning, data representation, and so on. Because what is the final problem, basically? Well, what we want to do? We have some semantic content, and you can put some abstract space. You have high-dimensional content. I put the title of the Plato's Cave because for people who are familiar with the allegory of cave, basically we have certain content, but we cannot even have access to this basically process. If it's a physical process, we don't know it entirely. It's different from the classical communication when I know the true distribution, when I know all the data, when I know the code book. Here we have a physical phenomenon, okay? And we have to discover it. We can even, for certain reasons, I can only see measurements of that, observations, not the entire one, okay? A representation of this. So this is a high-dimensional space, which I have to do probably to bring into some low-dimensional space where I know more or less how to transmit information. I have to also do some feature selection. There's interesting interplays and trade-offs between the relevance and the fidelity of represented information. And then I will basically use, inspired by the generative models, use how close is the content, the initial one that I had here, with respect to the point that doesn't work, with respect to what I will produce. Because sometimes is that I don't care about the exact content. I get to have content that comes from the same distribution. And this is not a typical distortion. Sample by sample, I minimize the distortion. What I want is that the content coming from a certain original distribution and the distribution that I will have when I will estimate and put all the estimates and I have the distribution of the estimates, they are as close as possible. And this comes with statistical divergences. Now, this is the last slide before the conclusion. Just give me 1 minute. Now, this comes to bring us that one key differentiating thing and what semantic information can lead us is timing. In most of the cases that we try to, re-innovate and so on, we find that some old traditional tools are the foundations. Now, what is different here, it could be a differentiating factor, is timing. Because at the end of the day, what is this macroscopic, let's say? end-to-end system. We have a phenomenon, we have information which is generated at a certain point of time and space here. For example, an observer which is in the physical world. And I want to reproduce it on some other distant point of space, and we're going to reproduce it in a certain time because basically I can put your bounds, your maximum compression rate and the minimum time duration to send this information as ideal as possible. At the end of the day, what do you want to do is you want to synchronize the two ends. You want to have the state that I have, xt1, to be as accurate as possible, represented by x hat t2, but also to be synchronized, not to have any lag in terms of time, okay? If I want to have real-time system or digital twins or do an operation, okay? So this brings us to two concepts. First of all, time is relative. And so semantic information is relative because the big assumption we have in communication is that time is measured and the evolution of a system is the same all over the place. This is not going to be the case. So suppose that you have information generated at the A1, it has a given time step, but you have a clock on the other side that it does not, is defective, and it makes time, measure times differently. How fresh is the information, and now you can see that you have multiple leaks, will depend on basically with respect to what I measure the time and the time step. This is the same as in distributed system. You have two events measured with two different clocks. Which one comes first? Especially when the clocks are not the same. So this gets us inspired by the frames of reference that we have in relativity and all these geometries that we have. So we're building some theory here. And what's more here is that you don't even see the information directly. It's a base station that gets this, the sensor brings it to the base station, and the base station sometimes gives us the information. So there's a lot of things put in here. So depending where the observer is with respect to the timing frame, the frame of reference of the time, information, semantic information could change, okay? Because it changed the way, it changed causality, it changed simultaneity, it changed synchronicity. And this is the most promising, actually, argument. So basically, if you want to wrap up in a nutshell, if we want to support this distributed intelligence, basically, the connected intelligence, we need a new theory and tools, okay? And the goal-oriented semantic communication is probably one approach, one theory for the real-time autonomous systems. And the gains scalability. Basically, we can do our job, we can communicate efficiently with less resources, less energy, and basically more efficient in terms of computation, and then we can build scalable systems. And there's many, many open theoretical problems, very exciting, and many fruitful interactions with other fields as well. Thank you very much.
Professor Marios Kountouris.
Thank you so much.